webinar. It's on science, technology, engineering and mathematics. For those of you that don't know the acronym, that's STEM. And we're going to be joined by Russell Brown. Are you there, Russell?
Yeah, sure am. Peter, thank you.
And also Trevor Redmond will also be joining us. You there, Trevor?
Yeah, good evening, everybody. Good evening, Peter.
Now, just before we start this webinar, I just want to run a quick thing through everybody because when you're watching, you may find that or think some of these experiments might take up a lot of class time. I could probably get through 30 or 40 textbook questions in that time. But a while ago, I used to work at University in Melbourne, and I would catch the train to work. And each day, I would invariably bump into a former student. That's just the way it is, because I lived in the same local area as the students. And it was interesting because during each of those journeys, I was fortunate enough that the students would actually come up and talk to me. I didn't feel like a loner. And during that time, the students would discuss the sorts of things that they'd done in class. Now, it's interesting because they would remember the things that we actually did. And although I say this with tongue-in-cheek, I never had a student come up to me and say, I remember when we did exercise 4, question 1, left-hand side. That was the best moment I ever had in maths and or science. And yet, sadly, we spend too much time, I believe, doing textbook material. Now, you may think at the senior level, perhaps that's a little bit difficult to pop all of those things in, these activities. But the best results I ever got from a group of Year 12 students was when we did exactly that, because the big difference was they remembered the stuff that we did. And I think that's the key. And we're fortunate tonight to have 2 people that do exactly that. They do lots of these activities, and I think you will find in most of these cases these activities are very powerful in terms of communicating mathematical concepts and giving students the opportunity to show you what they know, which is another thing. Now, of course, at the start of this webinar, if you weren't fortunate enough to see it, you might have missed out on our picture of the Ferris wheel. Sorry, my attempted humour. And also crowd population from a student's intrinsic point of view. Not sure how we get population growth when they consider their previous generations. It seems to go backwards. One other thing which we're including in our webinars is a problem to solve at the start of the webinar. So if you've joined us early and you weren't sure what you could be doing, here's a lovely little problem, mathematics problem, where if we take the square root of 1 plus 1 times 2 times 3 times 4, it equals 5, an integer. And then if we choose the next one along, 1 plus 2 by 3 by 4 by 5, we get another integer solution. If we continue that theme, the next one is 19, the next one is 29. My question, of course, was, first of all, do these always produce integer solutions? It's such an elegant pattern. And finally, what would that horrible expression look like? 1 plus the square root of 1 plus 100 times 101 times 102 times 103. And although I'm a calculator sort of person, you can, and I encourage you to, do that without the aid of a calculator. All that being said, it's time to join our presenters, and that is Russell Brown. He's the first one that we're going to listen to. So I'm going to pass over to Russell while you ponder that earlier problem. And Russell, are you ready to join us there?
I am. Thanks, Peter.
You're welcome, Russell. That's it. Your desktop's coming through nicely. Thanks, Russell.
When you press buttons, you always have to just hope that the final result is going to work your way, and it has.
And it has. Yeah, beautiful.
As Peter mentioned, STEM, it seems to be the magic word at the moment. Nice and easy to say anyway. And you can have the glass half full or the glass half empty when you're actually treating STEM in the school environment. Well, not quite. This little webinar is going to have a look at STEM, but we're going to try and break it up into smaller amounts, try and make it easy to introduce. Definitions of STEM, it's a fairly straightforward one. This one is basically coming from someone called Elaine Hom, just basically saying that we're joining science, technology, engineering and mathematics just into the one applied approach. So rather than teaching 4 disciplines, let's try and bring them all together. Now, as Peter mentioned in the intro, we might think this is a little bit hard to do. I've been teaching mathematics and science for a long time, and I've actually, in the mathematics classes, I've used a lot of my science skills to bring science examples into the mathematics classroom, and the kids actually do enjoy it. So this one here, once again, the 4 bits and pieces, probably the easiest ones for us are science, technology and mathematics. This engineering one, we seem to think, ooh, not quite sure what I've got to do. You see this little clip on the right-hand side? TI, particularly TI-US, have formed many partnerships with organisations. For example, health departments, NASA, to try and do a lot of the STEM work. So later on, when you get your newsletter, you'll see websites like TI-Nspire, so you'll have math-inspired, science-inspired. If you go to those websites, you'll find lots and lots of tasks already written up that address STEM. A little bit of a worry here, some data from the US, basically saying lots of students just don't want to do STEM or don't have it as one of their career aspirations, even though they have got a proficiency in mathematics. And they find, if you ask them early on, yes, they're interested. By the time they graduate, that has dropped way back. Now, lucky we're not in the US because we're probably different. This is from the Office of the Chief Scientist in Australia here. It doesn't look as though we are different. This is our Year 12 participation rates in science and mathematics. You can see them all dropping seriously here. Biology, starting from a much higher point, but once again dropping around about the same rate. Our chemistry and our physics have dropped right down. Now, your mathematics, we're using the right-hand axis for our scale. Of course, it starts off at a higher rate because it's compulsory. But you can see that the level of participation in mathematics, either being optional in Year 12, where it is in some states, and also some students will be dropping from 2 down to 1 mathematics. So we seem to have a serious issue here. So STEM has come in worldwide to try and address this problem. So how are we addressing it? Well, the government seems to be wanting to throw some money away. They've just committed an extra $12 million for STEM subjects in primary and secondary across the country. They've already spent $5 million. I'm sure all of heads of departments know about that. They've seen it. So if you don't know where it is, and I haven't got a clue of where this money is, probably need to get hold of your local federal government member and see if you can access some of this money. The website here basically is just telling you that this money has been made available. Trevor, you're a head of department. Have you seen any of this money, or have the schools been told about it?
No, not really, no.
Okay. So it looks as though you're going to have to be proactive as a head of maths, head of science, head of technology to try and access some of this money. Nice opportunity to get hold and buy some data logging equipment, the TI Science kits, or some of the other vernier probes. So ideal opportunity to get hold of some money. Now this engineering component is the weird one, mainly because we're not comfortable with it, not quite sure what we've got to do. So basically, to make the job a little bit easier, lots and lots of people have made these flowcharts that help us understand a little bit more. This one here is just taken off the web. There's the address. So we can see design comes into us. We're going to build it. We're going to test us. We're going to improve us. Now the research, does that come at the end? Does it become at the beginning, or is it a loop? Another one here is the one that we used at the T-Cubed conference in the US earlier this year. I think it's quite a nice one. Identify a problem, do some research, design your task, create it, so perform it, evaluate your results, then have a bit of a talk about it, discuss. If you need to, you can just go back and redesign it and continue the loop around here, or you can go back and identify a new component of that problem. So that's the engineering process. We'll have a look at some of those examples later on. My suggestion is not to try and to approach the whole 4 areas in the one go. For example, if you're teaching biology, then it would be nice just to do a little bit of mathematics on some of the science data that you've got, and if design processes come into it, well and good, but just try and get started the easy way first. Toss out the X and Y and use real words. That's probably my first suggestion that you would want to do here. So this one here, for example, so there's our coloured moths. So a little bit of evolution here. So here's some data that's been given to you. So we'll just put it into a spreadsheet. So a little bit of mathematics, and we'll do a plot. For science teachers, or particularly those taking the biology classes, I'll probably just look at a plot like this, so that would be given to them in a test, and ask to comment on it. Well, I think we probably could go a little bit further than that. So once again, in our mathematics, we could actually look for some data, do the plots. Then we might say, well, where is it increasing the most? So under our menu, we can go to Analyze, add a movable line, and just put that movable line where you think it's increasing the most. And that will give you a rate of change. And of course, it's not X, and that's not Y of X, because we're referring to the dark moths, the number of dark moths here, and we're talking about per year here. So we do have a nice opportunity to talk about what that is as a rate of change. We can grab hold of this one, and once again, turn this graph around, or the line of best fits, and we can just have a look at these values. So just put a little bit of mathematics into some simple biology little tasks. So that would be my suggestion, just to get started on some of these. And looks as though I'm probably better off. So Monohybrid Cross, once again, a little bit of mathematics in here. So here we've got a hybrid parent, so they're carrying 2 versions of a gene, alleles, and the parent one, we're just going to use a random integer generator. So we're going to go from 0 to 1, we'll do it 100 times. So this will tell us whether it's a dominant gene or a recessive allele, I should say, rather than gene. There's parent 2, join them together. So we can do some nice little bits of mathematics with this. And so here's just a random generation. So the zygotes, we're adding those 2 from the egg and the sperm together, and that gives us our parents. And in here, we can just do a plot. And when we're teaching biology, here we're talking about the 1-to-1 ratios. Well, we can actually do that, a little bit of mathematics with that, just to make it nice and easy. So that joins a couple of the areas together, your mathematics, your science, and your technology. The engineering is probably left out a little bit just there at the moment, but it can actually creep in. So if we just minimize that one again. So we've got fetal growth there. So once again, you can see all of this information is available from the website. At the end of this session, this webinar will be recorded or placed on the web, and you'll have access to a lot of this material. So probably in the next few days, you'll be able to get hold of a lot of these worksheets that address this. So this one here, are you under pressure? This one is a nice one for your chemistry. It does allow an avenue for your engineering processes to come in, and basically we can just use second-hand data, or we can actually use real data. I do have a unit set up here. It's whether it'll actually work without any special guidance. We'll have a look. We might just have to go to our backup version here. Yeah, it looks as though we'll just go to our backup version.
Just while Russell's setting that one up, I can assure everyone that I have done that particular experiment before, and if you're looking at that pressure sensor, just reflect on that later on in this webinar, because Trevor's got a wonderful experiment that he does with his students involving balloons, and I'm now imagining, how could I integrate that pressure sensor with what Trevor's doing? So back to you, Russell.
Okay, thanks, Peter. This one here, because I've been running a few of these together and I've got a few already set up, there's some little bit of a conflict happening here. So basically all we've got is a syringe, and we just have that syringe attached to a pressure sensor and basically connected to a lab cradle, just an interface hooked into the computer or the handheld, and we just adjust the volume and it measures the pressure, and we just record them. So I've just got some information here, and I've just done a regression line on here. But the good thing about this regression line here is that we can see that I've fitted a power curve to this. So if I just go in here to my analyze and my curve fit, and basically what I've done is just chosen a power curve, and we've gone okay. So there's the power curve there, and you'll notice that it is a x to the power of minus 0.924. Now, what sort of mathematics would you want to do on that? Well, in chemistry, we just said it was 1 on x, or 1 on v, so pressure equals 1 on v. Here, we can actually see that this is a x to the minus 1, almost to the minus 1. So that's a reciprocal relationship. So there's our power curve, 1 on v. So just some very, very nice little work that you can do here. So there are our values, and I've just created a column here multiplying pressure by the volume, and we can find that it is fairly consistent here. We would expect that to be a constant. So we've introduced some mathematics now into what was just a fairly simple relationship where we're just showing that pressure equals 1 on v. We can do a little bit more. This one here is an absolute magic one for your Year 9s, Year 10s or Year 11s. So the setup here is I'll just have a torch, a light probe, and just a small little cart here. So this is just a wooden toy, and I just bring that slowly past this light beam. So it's recording here. So you can see over here at the top, where I'm pointing with my arrow, you see that there is plenty of intensity there, and as that cart blocks that out, you can see that it blocks it out straight away, and then when the cart gets all the way through, we can go up to the maximum intensity again. We can measure the time difference here. We know how long the cart is, so we can use that to work out our average speed. So some just very, very nice, simple little tasks that you can do there. So there it is there in real life, and
Now, just while Russell's going on to the next one, there was a really good one which was shared with me by a gentleman by the name of Gary Bass, who was really influential in my beginning days, same with Russell being very influential, in the importance of using this data logging. And he showed me a graph similar to what you have there, Russell. Only there was a lot more of those troughs in there. And then he said, see if you can figure out what this was a picture of. And I couldn't figure it out. And he said, okay, now let me show you. And he showed me a picture of the playground. And it took me a little while, and then I understood it. I'm going to call them one of those vomit comets. I'm not sure if people now know what I'm talking about. They were like a little capsule where you could sit inside with a metal steering wheel and make that little thing go round and round really fast, like a whizzy-dizzy. And, of course, it had an opening on either side. And the funny part was, of course, the light pulse changed every time it went through the opening. So what they were able to do was determine the revolution speed of that, as I called it, a vomit comet, because that's about what you'll do when you get out of it at those speeds. And I thought, that's quite clever. And then he said, let's compare that to the sorts of signals that they got when pulsars were discovered, just a constant beat on a radar. And I thought that's a lovely little way of integrating some basic mathematics with a scientific discovery. So, back to you, Russell.
Okay, thanks, Peter. I'll just close off a couple of these little dialogues here.
That looked like an interesting one that you had there, the sinusoidal one. Was that a light of any sort, perhaps? Oh, here we go. I won't give too much away, sorry.
One of the issues there, when you've got a lot of other documents opened there, particularly the ones that are using the data logging, it prevents new ones coming on. So I've just removed all of my other documents, and I've just put a light meter in here. So basically what we're having a look at here is this one here. A nice little task. This one will allow you to put some engineering aspects into it. We're actually going to have a look at a fluorescent light, and I'm lucky enough to have a fluorescent light sitting in front of me. So the interval, I'm going to set up this collection at 3/10,000ths of a second, and I'm going to go for 3/100ths of a second. So we're collecting very, very quickly here. Now, all of the sensors that I've used so far and that Trevor has talked about are available in the TI Science Kit, available through your normal calculator retailer, or if you contact TI in Melbourne, I'm sure they can loan you some of this gear. So what I'm going to do here is just set this up, and I'll just go to my menu and experiment. And my collection set up. Now here, rate per sample, I actually want to choose interval, and I want 3/10,000ths. And I want the whole experiment to go for 3/100ths of a second. So 101 points, okay. And now I'm ready to collect. So I'm just holding the light sensor near my fluoro light. There will be some light coming from my computer screen, but very, very quick collection here. So there's the data being collected already. Now, this one is quite interesting because if I didn't have any other light around, this here would be a sharp point down the bottom. So this is actually an absolute curve function, a modulus function, and we can actually do some measurements here. So if I imagine that peak there actually goes down because light intensity can't be negative. So if we think of this as being half of a cycle, this middle one continues down and then comes back again, I can actually, under my menu, analyze. I'm going to choose examine settings, and I'm going to tick position and delta, and the value of this is I can go from this point. Now, just imagine this is a trough, going right across to there, and we'll notice the change in X is 0.02. So that is one full wavelength. So if I now just insert a calculator page and just say how many of those full wavelengths fit in to 1 second, and that was 0.02, and I've got 50 hertz as my cycling that's taking place on that fluorescent light. Now, that's a little bit of the mathematics. I would suggest we need to go a lot further than that, and we'll actually go in and model this. Now, the advantage of modelling here, of course, is we can't just go and do a normal regression because it's an absolute function. So there's a lot more involved in that one than meets the eye, and it's a very, very nice one to do. So if I just start this up here, and there's the data collected, and there's a graph that I've put on there, and there's the function there. So basically, it's a modulus function, and I've done it in cos, in cosine. Once again, I like using cosine rather than sine for when I'm modelling these things. So there are some nice little bits and pieces that you can actually work through with that.
The other one that's good about that, Russell, is it's the opportunity to bring in a discussion on what is the period of that function.
Yes.
Of course, the period is for one cycle. And what we're actually seeing there, the students can just pick off the 2 pi divided by 0.02 and start figuring out the period there. But of course, they'll be out by a factor of 2 based on our definition of period. So it's a wonderful opportunity to bring in discussion on what is the period rather than students just going straight for the textbook approach of I'll get that number and apply it to my formula.
Yeah. So this whole experiment, as I said, takes 2 or 3 hundredths of a second apart from the setup. So you can just pass this around to the various students, and you can stand on the floor and just hold it in the direction of a fluorescent light on the high ceilings in some of these rooms, and it will still work. So it's an absolute magic little task, particularly for doing modulus functions, if you want to take that extra step rather than just working out what the frequency is there in hertz. Trevor, I'll pass over to you now, and you can have a look at some of the STEM parts.
Thanks, Russell.
Okay, I'll just...
Now, just while Russell's passing across to Trevor to get Trevor's screen up, I'll fill you in on another activity which I've done in the past. Unfortunately, it's not so easy to do anymore. Not because
Peter, can you shift that down, please?
Yeah, sure.
It's moving down but not holding for me. Yep. To Trevor.
So, one of the things that I used to do was I'd put the light probe in front of what would we call nowadays a CRT, a cathode ray tube monitor, but the same as what we had in the, well, dare I say, the old days of television sets. They're all digital now, but the original analog TVs and computer monitors were a great place to try this. If people can cast their mind back to the difficulties they used to have if there was a television on in the background of a movie scene, you'd see a strobing effect, a black line moving up and down, or up the screen in many cases. And they used to have what's called a synchronization cable to stop that happening. But in the original days, they didn't have that technology. And basically what it was is the electron beam is scanning across the television set, as it was, or the computer monitor, and the equipment that Russell was using then is quick enough to pick it up, because typically the refresh rate was about anywhere between 50 and 100 hertz, and you could see a peak in the brightness, followed by what could be best described as exponential decay, and then another peak as the electron beam passed by the light probe. And even better, if you plug 2 light probes in, put one at the top of the screen and one at the bottom of the screen, you would see the amount of time it takes for the electron beam to scan from the top all the way down to the bottom to produce the image. And it was a great discussion point for students, because they always believed that the picture was just thrown up all at once. But of course it wasn't. The mechanics of the old cathode ray tube was that the beam would excite the phosphor on the front of the screen, and it would scan across that screen producing the image as it went. And that was how it was done. And it was a great way to show students that that image isn't what you think it is. It's just flickers of light coming on and off, and your brain stitches it all together. All right, after that little interlude, we're over to Trevor, who's going to give us the E part in STEM, which would otherwise be STEM. So without the engineering, we'd have a funny acronym. So it's over to you, Trevor.
Thank you, Peter. Good afternoon, good evening, everybody. I just wanted to start off by having a bit of a chat about this rocket challenge. We, when we went across to the States earlier in the year, we had a play with this. So in this particular case, as Russell talked about, the design phase of the whole process where you're given some equipment. In this particular case, the students had to design a rocket, and they needed to try and use those materials to design a rocket that would travel straight up into the air and get as close as possible to the ceiling. And as part of the analysis process, they needed to think about, or we needed to think about the design that we were going to build and the equipment. And we didn't have to use all of the equipment. We could choose what equipment we were going to use. We were going to then test it by actually firing it at the ceiling and see whether it did what it was supposed to do. And then if it didn't, then try and refine it so that we could make it better, so that it would achieve the goal that it would be asked to do. Now, in terms of this sort of design analysis, and in terms of that Russell was talking about before, it meets all of those particular goals. But in terms of the mathematics or the science type thing, I guess it's up to the teacher to be able to pull that out. And unless we had some sort of equipment or something like that to be able to collect some data, basically building a rocket to meet those particular outcomes is a nice experience, but we want to be able to get more out of it than that, I think. So this is a particular task that I do with my Year 10s. And so in this particular class, they have to build a balloon car. And they have a styrofoam block for the body. They've got some styrofoam balls that they can use as wheels. They've got some straws that they attach to the block, and they run some skewers through the straws so they've got some sort of axle to allow it to move. They've got a balloon and some jets and some rubber bands. And so what their task is to do is to build a balloon car, but then it's also to collect data from that balloon car that will allow them to build a mathematical model to describe the relationship between the balloon size and the distance traveled. And so they need to then check their model that they've generated, and then they need to use the model and go outside the data set to see whether the model is useful. I mean, it's well and good to build a mathematical model for the data set that you've given, but what you want to know is how good is that model when you apply it outside of the data set. So when they build the balloon car, it's not just a case of whacking all these things together and see what happens. So here's a video of a trial. And you'll notice that there's some problems with that particular design. So just because you've put it together, it doesn't automatically do what you expect it to do. And so even in the design phase, you still have to go through and you have to think about, refine it and that sort of thing. And so this is after playing around with it and moving the balloon backwards or forwards a little bit, you're able to get a much better scenario. And so the students then needed to, once they've collected their data, and they needed to repeat this a number of times because they needed to look at the size of the balloon. And of course, the distance traveled is going to be the dependent variable, and that was stated in the task. But the students had to decide what was the independent variable. So they had to think about what size of the balloon are they going to measure. So are they going to measure the circumference of the balloon? And of course, there's inherent problems with that because they might make an assumption that it's a sphere, and clearly it's not. But where do you measure it? And so they measure like at the equator, like through the middle of it. But if you measure a little bit off that, then it's going to change and it's going to vary. So there's some precision associated with that. And even when they wrap a tape measure around it, what they're going to do is distort the balloon. So the measurements that they get, there's some variability in terms of the actual circumference that they measure. Or alternatively, they could try and measure the diameter of the balloon. And again, of course, how do you measure the diameter of the balloon? And so the students have to decide what they're going to measure and how they're going to do it. So there's a lot of thought involved in terms of building the car, because there was no design as such. I mean, I showed them a picture of what they could do just to give them some ideas about that, but it was up to them. I mean, last year some kids drilled holes through the styrofoam block and put the straws through the middle of the styrofoam block and run the wheels through the middle. Nobody did that this year, but there's certainly different ways that they can do it. So let's have a little look at some data that some kids generated. Okay, so let's get rid of that. All right, so here's some data of the diameter of the balloon and the distance traveled. And there's lots of different ways that they can analyze it. Like they can do a scatter plot in a graphing screen. I'm going to use a data and statistics screen, so we're just going to insert a data and statistics screen. And so we need to put the independent variable down here, which will be the ball diameter. And we need to put the dependent up here, which will be the distance traveled. And so if we have a look at that, then we can see that there's some sort of mathematical relationship there. Now, these kids are grade 10, so they have a reasonable understanding of linear functions. They're starting to maybe build an understanding of quadratic functions, but they're probably not there. So in terms of the models that the students will build, the mathematical models, they're probably going to go to where they're most comfortable. And if you look at the trend in the data, it would be reasonable for the students to be able to build an argument for there being a linear trend in there. So what we can get, the other thing with the data is we would expect that the curve or the line would actually pass through the point 0, 0. If you stop and think about it for a bit in terms of the context, there is, if there's no air in the balloon, then the balloon's not going to go anywhere. But if we add a movable line to this, okay, and we play around with it a little bit and we get it to where we think might be a reasonable place. And so the students can do this. I ask the kids to do that, to add in a line of best fit and decide where they would build it. Then they would need to go away and apply the mathematics to that particular model and build it. And I also asked them to look at the critical values that are associated with it. And as I said, that we would expect the balloon to pass the curve to pass through 0, 0, and it doesn't. And so then one of the things that's really important is to look at the model that you're building and the context from which it comes, and try and make some sort of look for consensus between the model that you build and the context from which it comes, to try and make some sort of sense of it. And so the question then becomes is, why does it not pass through the point 0, 0, but passes through, say, this point here, say 0, 25 or 25, 0? And if you stop and think about it for a little bit, it does make some sort of sense, in the sense that the balloon car has to overcome the internal friction of the system. Like you've got friction between the axles and the straws, you've got friction between the tyres and the carpet, you've got the mass of the balloon that's constantly changing, and those sorts of things. So it's not going to pass through 0, 0. In fact, if you were to make the diameter 20 centimetres, the balloon wouldn't move. It's only when it gets to around about over 25 centimetres, so there's that much air in it, that it's able to overcome the friction in the system and allow the balloon car to start to move. So the students need to think about these sorts of things. The other things that they need to think about is, when they're collecting their data, the other variables that are in the system, like for instance the carpet. Now, the students will probably assume that the frictional forces are uniform, and the way they can control that is by running the balloon car across the same set of carpet. And in doing that, then while the frictional forces within the system are changing all the time, by running the balloon car over the same set of carpet for each trial, those frictional forces will be similar. The other problem, of course, is the balloon is constantly changing its mass, so the mass of the car is changing. And so another assumption that the students need to think about is the fact that, maybe the mass of the car is going to be uniform. So there's all of these things that the students need to think about in terms of building their mathematical model. All right. So this is one of my, this student, she looked at it from a different perspective. She built the linear model because she was asked to, but when she actually went through, she wasn't really happy with the notion of circumference of the balloon or diameter of the balloon. And so what she wanted to do was look at the volume. And so she collected data in terms of the distance traveled versus the volume of the balloon. And she noticed that there was a real curve in the data. And so what she did was she thought, at this stage, she had a pretty good understanding of transformations of quadratic functions. And so she assumed that the turning point was, first of all, minus 200, minus 200. And she built a model, a quadratic model based on that. And she found that that didn't work. So she adjusted it back to minus 300, and she was able to build a model. Now, what's really nice about this was the fact that she built the equation in terms of a function of y. So x is equal to a times y minus k all squared plus h. And so she was able to build that equation, and we talked about, well, how could you possibly graph that? And of course, with the TI-Nspire, if you put in a text box and type the equation into the text box and then drag it onto the y-axis, the calculator will automatically graph it. And so she was able to verify how good the model was in terms of, visually anyway, verify visually how close the model fitted the particular data set. And so once she had that particular equation, then she was able to work backwards and then express it in a form that we're used to in terms of function notation, which was y as a function of x. And so she ended up with plus or minus the square root of x plus 300 over 0.0033 minus 300. And of course, she decided, which is quite true, that we reject the negative solution because we're only interested in the solution that's in the first quadrant. And so we had a particular model. Now, one of the things we talk about with the kids is it's nice to have a model, and quite clearly, visually anyway, it fits the data. But what we want to be able to do is to verify mathematically how good that particular model is. And so what we could talk to the students about is if you build a model by hand, of course, if you use technology, then you'll get an R squared most of the time. But if you build it by hand, then how do you verify it? And one way to look at it is actual versus predicted. And so what you can do is graph actual versus predicted, and you can look at the relationship and see how close that is to the line y plus x. And so in this particular case, she had a slope of 1, she had a y-intercept of pretty much 0, and she had a pretty strong linear relationship with a high R squared value. And so she was able to build quite a strong model. So in terms of the sorts of things that the mathematics that students can bring to these types of tasks, it depends on their understanding, it depends on where they are, but it gives the students the opportunity, those really good students, the opportunity to be able to demonstrate how thoughtful they can be, and to be able to access some really powerful mathematics in order to build mathematical models. And of course, one of the things we want the students to be able to do is to refine their models. And so in this particular case anyway, she refined it from a linear to a quadratic. In the previous one, where the students were just building linear functions, students could have what they talked about was finding the slope between all of the points and then looking at the average slope. And by average slope, they could be mean or median slope, and then build the equations based on those and see how good they are. So it's about getting the kids to be thoughtful about the context and looking for consistency between the mathematics that they generate, and also, from our perspective, the mathematics they generate and the context, but also being aware of those other things, like, for instance, the friction in the system, by being aware about the masses changing and those sorts of things. They can't model those, but they can be thoughtful about those and look for ways to maybe overcome them. The second task I want to have a look at is to do with the charging and discharging of a capacitor. So here we have a 220 microfarad capacitor with a resistor and a power source, a battery, which we can charge it up. I'm going to use something a little bit different. This is the structure, the breadboard that I'm going to use. I mean, science departments have these, and you can borrow one of those from the science department. And it's the same sort of setup. You've got a resistor there, if you can see it. You've got another one over there. You've got your capacitor in the middle, and I'm going to use the voltage probe to collect some data off that. In this particular case, I set it up so that I can collect data from it charging. So when I can connect the wire to that diode, The point of the diode is it allows me to see when it's charging, and then if I touch it on this one, it'll discharge. And so I can see what's happening to the capacitor, whether it's charging or discharging. And there's a fair bit involved for the students in terms of putting something like that together. So they would need support with that. They wouldn't you just wouldn't be able to necessarily throw that at the kids and get them to build that sort of particular thing. But in terms of creating circuits and those sorts of things, they can follow a diagram, and they are able to put that together without too much trouble. And then they're able to collect the data. And from a mathematical perspective, that's what we're interested in. All right. So if we have a look at a situation, we'll see what happens here. All right. So I have got some data there that we'll have a play around with if things go pear-shaped, but we'll have a little look here. So we've got a voltage probe. And you can see that it's been connected up. So to make this thing work in this particular case here, if we click on that, what we can do is we need to make the samples about 25 samples per second. And if we're charging up the capacitor, then we can do that probably in about 4 seconds or so. And so we just go OK. All right, so let's have a look and see how we go. So at the moment, we can see that our capacitor is discharged, so that's good. And what we're going to try and do is we're going to try and charge it. So if we click on there and we plug that in. Okay, so there's one that's been charging. If you don't like it, you can run it again, but if you do like it, and we'll keep that one because that's not too bad, we'll select that. All right, so the other one we want to do is we want to see what happens if we discharge it. So if we collect another data set, and if we click there, and plug that in, okay. And so we have that particular data set, so that's not too bad. Sometimes what happens is you've got a translation along the y-axis, along the x-axis, and so you've got to take that into account in terms of your modelling, but we don't need to worry about that.
Just a tip for those people that are looking maybe at an advanced thing, I'm not sure whether you did it, is that you can set it to auto-detect a decrease in voltage or an increase in voltage, and that's a neat way of doing it. Another thing that works really well I've done in the past prior to this activity is an M&M task, which I've now substituted Skittles because they don't have any nuts in them, and that is where you put them all in a container and shake them up, and the kids get to eat all the ones as it was before with the M&M facing up, or now with the Skittle sign facing up, and you get an exponential decay based on the number that were there present at the start, and then you get roughly half with each manipulation of the cup full of Skittles, and it works out nicely. And the one that Trevor's just done here also works out nicely if you kind of doctor the resistor and capacitor amounts and do your data collection at a sampling rate of 1 per second. It's a nice way of just looking at the successive ratios as the capacitor discharges, and you can get the equation for it very quickly from that ratio, and it reinforces that exponential has a constant ratio between successive terms. Sorry, Trev, back to you.
That's all good. Thank you. Well done. Now, what's usually most people do now, or what kids will do anyway, because they've got this data, and I'll choose this one because it's probably the easiest one to have a look at, I guess, is they'll probably do an analyzer, which is fair enough. And then what they'll do is they'll do a curve fit, and we're looking at, I've got two of those. Let's get rid of one of those. Sorry, just give me a minute. No, that's not the one. That's the one. Get rid of that one. There we go. All right, analyze, and we're going to do a curve fit, and we're going to do an exponential. And, of course, we do that. We get something that looks like that. And, of course, you know, the question is, why do we get something that looks like that? And the problem, of course, is that in this particular capacitor, there's some sort of residual charge. And so when we do regression analysis, it automatically defaults to the x-axis as being the asymptote. And so it builds the equation based on that. And so in this particular case, we don't get a very good model. And so that becomes then a problem, of course, what do we do? And of course, what's really nice about this is the fact that, if we want to read that, what we can do is we can add in a model. And I've only sort of found out about this really recently. And I like this really nicely because what it does is it allows, or it forces the students to think about transformations. And I think that's really, really nice. So if we choose an exponential function now, in this particular case, we don't have a translation along the x-axis, so we don't need to worry about an x minus c. But we do have a translation along the y-axis, so we do need to add a plus d on the end of it. And then we can see what happens. And so if we go OK, what we can do is we can give some particular values. So if we click in there, now in this particular case, a value, we'll start off with, say, 9.2 or something like that. Not 92, 9.2. It's going to be too high, but it'll give us something to start with. The increment is when you adjust it. That's how it adjusts. So it'll adjust by 0.1 each time. The b value. Now, I've played around with this before, so I sort of know that it's probably going to be somewhere around about 0.02. So we'll start with 0.02 just to make things a little bit, save a little bit of time. And if we have a look at the asymptote, all right, so it said 1.59. I don't know where that came from. That's sort of a bit interesting, but I mean, if we have a look at there, it's probably, we'll start with that and see what it looks like, and then we can adjust it later. And so we can go to that. Oh, look at that.
That's not bad.
That's really sad.
You're going to spend 5 minutes trying to get it to fit better, weren't you?
I was. I wanted to go through the whole thing. Look at that. How nice. How nice is that? So, I mean, the point is that if we have a look at this, and what we can do is, I wonder where the model usually comes up there. I wonder why I didn't.
Probably because you
there it is. There we go.
In the first place.
There we go. So, I mean, what the students should be doing is looking at, like, you can adjust it a little bit in terms of the problem with 4 seconds with a decay is it takes a lot longer than that to be able to get to the data. And of course, there's a residual, as I said, there's a residual charge in the capacitor. But hey, I'll take that one as a win.
Trevor, that model that you've just used is also ideal for Newton's cooling curve.
Yeah,
where there's
absolutely.
the ambient temperature is there, which means the D value is nice and easy for them to work out just using the ambient temperature. So another nice little approach.
Sure. I really like this modelling feature. I mean, like I said, I only discovered it very recently, and it's just so nice because regression is nice when the kids have a really good understanding of the concepts. But in this particular case, regression wouldn't work, so they have to come back in a different way. And so what's really nice is they have to look at the data, and they have to decide, okay, well, what is the most appropriate model in this particular case? And so then they need to look at that, what the maximum value is, or what the value is at the y-intercept, and those sorts of things. So there's some really nice things, and it really forces the students to use their mathematics in a meaningful way. And of course, it's accessible to everybody. Like, for instance, I mean, I sort of had a bit of the experience, but I mean, even if, say, for instance, I made that, I don't know, let's say I made that 0.9 or something like that, okay? So the students then see, okay, visually, the graph's not doing what I need it to do, so how am I going to change that so that in order to do it? So I'm going to have to change the degree of curvature of or decay of the exponential function, and so I can manipulate that. So even at the lowest level, a student, all they need to do is sort of, at least they can just drop that, well, not that far, but I mean, change the spin value. Like, for instance, if you want to sort of modify your model, you can change it and modify it and do all sorts of really cool things with it. But yeah, so that's sort of really nice. So if we have a look at, we'll see if the other ones works as well, very quickly, if we've got enough time, we'll see. All right, so let's have a look at run 1. Get rid of that one. Get rid of that one. Keep that one. All right, so we'll leave the model there. That's fine. So in this particular case here, we're going to have to use a different model. So again, the students have to choose the model that they're going to choose. So it's going to be an exponential function again. All right, but in this particular case here, it's going to be a2 minus a2 b2 to the power of x. And again, there's no translation along the x-axis, so we don't need to worry about that. So we can give some values. So in this particular case, if a is going to be, I think it's about, what was he saying, 9.2 or something like that. B, in this particular case, is going to be somewhere around about, let's say 0.9, 0.9, not 9. That'll cause a stir. Oh yeah, that's right. There we go. And then if we go OK, so what do we got?
You're going to pick up model 2, I think. You've got model 1 showing. Is that model 1 showing?
Oh, we got to get rid of that, do we? Okay.
No, you've got model 1 showing.
Oh, okay. Get rid of that. Thank you. Model 2, there we go. Oh, it did that before too.
Oh, it
9.2. Yeah. What? 9.2. Where are we? There we are there. Let's get rid of, just give me a minute, sorry. I know we don't have time, but anyway, let's move model 1. There we go. So we've got, what's that value there? So that's 9.5. So let's make that, say, 9.6. And let's change that to 0.6. No, nearly there. Getting better. I don't advocate this sort of thing, but... Point.
It's just a 7 a day.
0.02. Yeah, there you go. Look at that. Yeah. Thank you. There's a bit more thought than I would have been there. All right, so again, the kids have to do it. And of course, they can go through an iterative process like that. People call it trial and error, but in mathematics, it's an iterative process. It's trial and refine. And so they can come up with a better model. So that's sort of pretty much all I have. Russell, I'll give it back to you now. Is that right?
Yeah, that's very good. What I'll do is I'll grab the presentation back, and what I'm going to do is spend 1 minute. I think we've got 1 or 2 minutes left. We have 1 or 2 minutes left just to show one of the questions that was in the opening introduction. And the reason why I'm really keen to show everybody this solution is somebody in the chat space, Sanjeev Meston, a teacher from Victoria, gave me a really
Peter, can you just transfer that to Russell, please?
No, that's all right. I've dragged it onto me. I can pass it across to Russell.
Oh, you there? Okay.
Yep.
Oh, good. Sorry.
That's all right. So just on the screen at the moment, you'll see that's the problem that was given in the original opening slides, but of course there was numbers there for n, and I've just put a slider in there, so that's equivalent to the square root of 1 plus 1 times 2 times 3 times 4, and then we can change it and see that we will get an integer solution. That doesn't prove that we will always get an integer solution. Now, the chat space, Sanjeev showed me a beautiful thing, and he did a very good job to put it into text. He said, just take the average product to the first and last and then the middle two. So you'll see in my little solution there, I've followed what he's done. First term, n, and the last term, n plus 3, found the product of those, found the product of the middle two, divided by 2. So these are not big numbers that we're working with here. This is like 7 times 9 and 7 times 10 and 8 times 9. So they're not large numbers that we're working with, but I can assure you the square root of some very large number equals 71. I wouldn't have been doing that by hand in a hurry. And it means that the problem that was originally posed becomes somewhat easier if we're just multiplying 100 and 103 and 101 times 102. They're not too difficult to multiply. So that's a lovely, elegant solution that he's come at there without having to find the product of these four numbers. And the only thing that I wondered then was, how does that prove the result? It's a lovely, elegant demonstration of what we can come up with. So what I did was looked at it algebraically, and if we have a look at the original expression without the square root sign, it's 1 plus the product of four consecutive numbers, well, four consecutive integers. That gives you a rather large quartic. Now, if we assume that this is going to produce a nice perfect square, because we seem to be coming out with integers, and therefore we'd want a perfect square here, it's actually quite easy to factorize, because the first term has to be an x squared, the last term has to be a 1, and then the next term to look at is actually this 6x on the end, because if you expand that quadratic, the only way we're going to get x terms is through this middle one here, of which there'll be 2, so that has to be a 3x. And if I want to expand that just to check whether I factorized correctly, we get the quartic that we started with. Of course, we could have just typed in factorized. And because we've got a perfect square here, then the square root of that would just be x squared plus 3x plus 1, which means our original problem that had 1 plus 100 times 102 means you'd have 100 squared plus 300 plus 1, 10301, would be the answer to that horrific problem that was given at the start. So that's a nice little demonstration of how we can use algebra, but really love Sanjeev's suggestion there of finding the product of the first and last and then the middle two and averaging them out. I now have to go away and figure out, why does that work? That will be my homework. Now, we're about out of time. I want to pass a great thank you to both Russell and Trevor for sharing their wisdom and their experience using data logging in the classroom. And I think everyone would agree that there's quite a lot of mathematics that sits behind it. It's not just a matter of plug and play and put a graph on there. There's quite a lot of mathematics that sits behind what these guys are doing. And not just mathematics, there's some science, there's some technology, and obviously some engineering thrown in there as well. So
now, the TI Science kit, Peter, if you mention that, that includes a motion detector that does motion, velocity, acceleration. You have a pressure sensor, a force sensor that does mass, density, force, and momentum, voltage, light, temperature, pH, a lab cradle. So they're available as a kit from your calculator distributor, or if you contact TI, if you want to have a bit of a play around with them, I'm sure they'll loan you those. We'll also provide a lot of step-by-step examples on how to do anything that you've seen on the webinar tonight. Thanks, Peter.
All that will be available for download. And thank you, Russell. And also thank you to Trevor, who I'll be catching up with in Brisbane tomorrow. You there, Trevor?
Yeah, thank you very much. This was fun. I enjoyed it.
Okay. Thank you very much, everyone. And we hope to see you on our next webinar very soon. And that's all.